Hello, everyone. Today we're going to talk about the uniform random variables and uniform distributions. A uniform distribution is kind of unique in the sense that its density function is constant on an interval. So, for example, if we have a random variable x, which is, say, uniformly distributed from A to B, then fx, the density, is a constant on A, B, and zero otherwise. Okay, that's the definition of a uniform distribution. Using the fact that this density function is a density function, the function is a density function, and we're able to figure out C. So basically, you integrate uh, C from A to B dx. It's a constant, antiderivative Cx, and then x runs from A to B. That equals C times B minus A. And we know that is 1. So C equals 1 over B minus A. So that's our density function. All right. So we know what C is as long as we know the interval. So we got fx, and how about the capital Fx, which is the CDF? So cap capital Fx is defined to be little f of t dt from negative infinity to x. And then assuming fx, the density ft or fx is c on interval ab, when we plug in, so 1 over b minus a, we need to be very careful about the lower limit, which is actually a, the upper limit, which is x. Okay, so be careful here. You have a negative infinity, but you need to change to a because the density is 0 otherwise. And then we have 1 over b minus a times t, and t runs from a to x. So that equals x minus a over b minus a. Okay, that is when x is greater than a less than b. And when x is greater than equal to b, it's fx equals 1. And fx equals 0 when x is less than equal to a. All right. So in terms of the graphs, okay, and I have a, say, just put them together, okay? Say you have a y, you have x, 0, orange, okay? And also y, x, orange. And then you have a here and b here. Then the PDF 1 over b minus a would be a horizontal line segment. It's a line segment and 0 otherwise. You don't really need to do something like this, but if you want, that's okay. It will be 0 otherwise. The A and B, the boundary of the interval, whether you should treat uh, which one solid point, which one is empty point, really depends on how we define this interval to be open or closed. Okay, so now here is open, then we would have say empty circle here, empty circle here. Okay, this is not very important. And because uniform distribution on that one is also very similar, you will have a solid point here. Okay, so again, it's not an important issue for the moment. And in terms of CDF, look at the CDF. I hope that you realize this piece is actually a linear function. So it looks like this. All right, and then you do this. When x equals b, obviously it's 1. And then you have a horizontal line again. And this, it's 1. Okay, that is where this horizontal line, the y value is 1. Okay, so this is a little fx, the density function, and the CDF, the cumulative distribution function. Next, let's talk about the parameters. Expectation and standard deviation. Say again, x is uniformly distributed on A, B. And we know little fx equals 1 over b minus a, when x is greater than a, less than b, and 0 otherwise. Expectation, which is mu, is defined to be the integral from negative infinity to infinity x times fx dx. And then you plug in 1 over b minus a, so I'm going to change the lower limit to a, the upper limit to b. And we have half x squared, antiderivative, x from a to b. And you have 1 over 2 times b minus a times b squared minus a squared. This is the difference of squared, just difference of squares. So you have it equals that. And then cancel out b minus a. We have 1 over actually a plus b over 2, which is the average of the up two values, which are endpoints of the interval. It should make sense to you because when we look at the PDF, so this is A, this is B, and you have this 1 over B minus A here. And then the mean is when it's the point where you put a wedge there, the whole graph will look balanced. So it's just half the middle point of A and B, which is exactly half of A plus B. So that's our mean. This is symmetric with respect to, and the PDF is symmetric with respect to its mean. All right, let's look at the variance. Variance is the second moment minus the first moment. Let's calculate the second moment, which is integral from a to b, x squared over b minus a, okay, dx. So I already changed the lower limit and upper limit from negative infinity to a and positive infinity to b. X squared times density, I put them together as one fraction, that's no problem. And then you have 1 over b minus a times 1/3 of x to the third. X runs from a to b. And then you plug it in. And be careful with the, not be careful, I mean, notice the difference of the cubes. So it's 1 over 3 times b minus a times b to the third minus a to the third. We do have a formula for b to the third minus a to the third. Basically, you factor out b minus a. You let b equal a, you get 0, that means b equal a is kind of a root. So if you consider x minus a to the third, sorry, this one, uh, you let x equal a, then you get 0. That means you can factor out this term as something else. So in fact, this something else is pretty easy to get. You can do the long division or synthetic division or whatever. It will be x squared plus 2, not 2a, plus ax plus a squared. Okay, you can really expand the product and you would get x to the third minus a to the third. There are a lot of cancellations, so you can check it by yourself. Anyway, I have this 1/3, b minus a would be canceled out. So you have b squared plus ab plus a squared. That's our second moment. And then we have the variance, which is the second moment minus the first moment squared. So you have 1/3 times, let's change the order. It doesn't really matter. It's just, I guess, I like a square first. Minus, remember expectation is the average of A and B. So you have minus 1/4 A squared plus 2ab plus b squared. Okay, you have a plus b squared. Putting them together, you have 1/12. And I have 4a squared plus 4ab plus 4b squared minus, I multiply by 3. 3a squared minus 6ab minus 3b squared. Okay, so eventually you will get 1/12 times a minus b squared. You have a squared, then you have a b squared. Sorry, I forgot the 4 here. I mean, these two numbers, you put them together as a find a common factor, which is 1/12. So you move out 1/12, you will leave 4 for this term and 3 for this term. Okay. If you don't understand the algebra, I'm gonna quickly do something like this: x plus 1/4 y. So I move out 1/12, so it's like 4x plus 3y, something like that. It's some simple algebra, but if you don't get it, try to understand it, okay? All right. So this is our variance, which is a minus b squared over 12. And then the standard deviation is the square root of the variance. They're always non-negative. So I have a minus b over square root 12. If you want, you can simplify a little bit further. What is that? So a minus b times the square root of 12 over 12 by square root of 12 equals 2 times square root of 3. 2 times square root of 3. 2 is canceled out. You have a 6. Okay. And normally it's fine with that. In terms of a calculation, sometimes it's good enough to have a minus b over square root of 12. Okay. So that's a variance. Let's have a look at an example. So x is uniformly distributed over 0 to 10, this interval. Calculate the probability that A, B, C, and so on. Okay, let's do that. So the density fx equals 1/10 when x is greater than 0, less than 10, and 0 otherwise. Okay. Normally we don't need to specify that again, 0 otherwise. Okay, but it's assumed. If you want to specify, that's totally good. That's fine. You can work with the interval. That's no problem. Sorry, you can work with integral. That's what I mean. X greater than 3, so it's from 3 to 10. 1/10 is the density, and dx, you have a 7/10 is 10 minus 3. And b, x greater than 6, so it's from 6 to, oh, hold on a second, I think it's less than, I forgot it's less than, so let's redo it. Okay. It's from 0 to 3. And you would have a 3 over 10. From 10 to from 6 to 10, you 1 over 10. That is 4 over 10, which is 2 fifths. C from 3 to 8, 1 over 10 dx, you have 1/10, then you have 8 minus 3, which is 5, so it's half. This is just using the integral. That's no problem. Or if you want, you can use a geometric approach. It's pretty simple as well. Actually, I hope that you uh, sort of be familiar with both because that helps you understanding this model. Okay, so I have this density, it's constant, which is 1 over 10 and 0 otherwise. Okay, so now suppose I wanted to find out the probability that x is greater than, so less than 3. So you have 1, 2, 3. Basically, it's asking this area. Okay, that is, the area equals the probability of x less than 3. But it's also it's a rectangle, and the height is 1/10, and the base has length 3, so it's just 3 times height, which is 3 divided by 10. X greater than 6, 5, 6, 7, 8, 9, 10 squeezed. So there's 3, 4, 5, and greater than 10, greater than 6 from 6 to 10, you also have a square, rectangle, and base is 4, and height is 1/10. So this area is probability of x greater than 6, which is 4 divided by 10, okay, again, 2 fifths. Now, from 3 to 8, it's very similar. Okay, 3 to 8. Three is here. That means the probability is 8. Is the area of this rectangle with base length 5 and height 1/10. So that's half. Okay. All right, I think we are okay with this problem. Let's move on to the next one, which is a little bit more complicated. Buses arrive at a specified stop at a 15-minute interval starting at 7 a.m. What is they arrive at 7, 7:15, 7:30, 7:45, and so on. If a passenger arrives at the stop at a time that is uniformly distributed between 7 and 7:30, find the probability waits less than 5 minutes for a bus or more than 1B, more than 10 minutes for a bus. I would like to draw a timeline to sort of make the information clearer. Okay. So this is our sort of probability. This is the time, 0. Let's treat origin as a 7 a.m. So I have a 7:30 a.m. And the density could be 1 out of 30. I think it should be totally fine. Okay, 1 out of 30 because you treat minutes as like a unit. So you have a 30-minute interval. So the density is 1 out of 30. Okay, so I'm going to draw something like this. Now, the bus comes at time this time 7 o'clock or 7:15 or 7:30. Now we need to analyze the question. Find the probability that he waits less than 5 minutes for a bus. So less than 5 minutes. After 7 o'clock, obviously when he arrives, um, from 7 to 7:30, the bus is assumed to be gone already. I mean, the 7 o'clock bus should be already gone. And the probability that the person arrives at exactly 7 a.m. would be considered zero because we're talking about continuous distribution, the probability. Well, we don't need to worry about 7 o'clock issue. So, in order to wait less than 5 minutes, the person has to arrive less than 5 minutes before the bus arrives. So bus arrives at 7:15 and 7:30. So the person has to arrive after 7:10 or after 7:25 with both time time interval, which is 5 minutes. So the area would be 5 times 130 plus 5 times 130. That's one third. Get 10 over 30, that's 1/3. Let's study B. More than 10 minutes for a bus. More than 10 minutes. Okay, so this is 7:15. More than 10 minutes, that means the person cannot get to the station before 10:05. So I'm sorry, cannot be after. If it's after, then the waiting time will be less than or equal to 10 minutes. So the person has to arrive to the station before 7:05 and before this is 7:20. Okay, so the person will have to wait more than 10 minutes. And the area again, it's 5 times 30 plus 5 times 30, it's again 1/3. All right, so that is about uniform distributions. It will be used sometimes incorporating with other distributions. In the distribution itself, in this class, it's relatively easy. So I think that's about it. I'll see you the next time. Bye bye.